So in this video, I'm going to demonstrate the use of a parallel analysis engine that I located at this website right here. It's analytics.gonzaga.edu/parallel engine /. And so at any rate, one of the downsides with SPSS when you're running factor analysis or principal components analysis is that there's no system for running parallel analysis. So you have to kind of come up with some alternatives. One of the videos that I came up with yesterday demonstrated the use of Brian O'Connor's syntax that you can download from his website for carrying out parallel analysis. And this is just kind of an online engine that you can utilize as well to carry out the analysis. So using some of the data that I have been using in a couple of other videos, what this is basically individuals' responses to a set of items from the International Personality Item Pool, and more specifically, they're coming from the CAT personality disorder scales, with items that we're measuring affective lability, anger, anxiousness, depressiveness, grandiosity, and health anxiety. So at any rate, what we're going to do is just demonstrate the use of the engine. First, let me just kind of note up here what you're going to be putting in. So it's already has a set of defaults in here. The first piece of information that you want to include is number of variables in the data set to be factor analyzed. So you're going to type that in. The sample size for your data set. The type of analysis, which you actually have two options. You have principal components and factors right here. So then the number of random correlation matrices to generate the eigenvalues. And so right now the default is set at 100. You can increase or decrease it. Also, you have percentile of eigenvalues. So what you'll notice is in the output over here, the defaults, you'll see it says mean eigenvalue and percentile eigenvalue. So you have the option of selecting a given percentile for the eigenvalues from the randomly generated correlation matrices. The default is 95, which is currently one of the more conventional percentiles that folks are using. And then you also have a seed number as well, so you can change that as you need to. So at any rate, let's run our analysis using principal components, and then also we'll try the factors approach. So our data set actually has 39 variables associated with it. And so I've just changed that. The sample size for the data set, the list-wise sample size is 463, so I will just hit that as well. And so you can see that as you change the specifications over here, the values over in these columns change as well. So at any rate, what I'll do is just quickly go to Analyze, Dimension Reduction Factor, and we're going to move all of the variables over. And really quickly, you'll see that the variable names are Q1. They actually range from Q1 to Q49, but actually they increment by 1 up until about Q29, and then it increments from that to 40. But so basically there's, as I said, there's 39 variables in this data set. So just really quickly too, I'll go to descriptives and ask for that. And under extraction, we'll leave it as principal components. And you can see you have your usual options as well. And then we'll just click on OK. So you can see, again, the list-wise N is 463. It's the same all the way across. And as we scroll down, you can see that we have our communality table and so forth. But the main part of the parallel analysis is involving comparing the eigenvalues from our data against randomly generated eigenvalues. And so what we have with our engine right here, basically what's going on is that we generate essentially 100 random correlation matrices, under the assumption that the relationships among the variables are orthogonal. And for each of those correlation matrices, you would have essentially a computation of the eigenvalues from those matrices. So for, let's say, for the first simulated matrix, we would have essentially 39 eigenvalues that are computed based on that matrix. Then you would have a second one, same, third one, all the way through 100. And then the mean eigenvalue column is basically capturing the mean of all of the eigenvalues for each component across those 100 matrices. The percentile eigenvalue is the 95th percentile of the eigenvalues. So basically what we do is we can just go into our output right here, and these eigenvalues are basically from a PCA, the PCA right here. So we don't really want to compare with these eigenvalues. Right now these are still from the PCA. It's just that the eigenvalue cutoff rule, which was the default in SPSS, was invoked, and so you can see that only the eigenvalues that fall above 1, those components are all retained, so you don't see any further eigenvalues that are printed out. So it's really just worthwhile to focus in on this column right here. So as you can see, the first eigenvalue from the principal components analysis is 10.549. Second one is 3.502. Third one is 2.68. So if we go to our little engine right here, you can see that, and we're going to focus in on the 95th percentile eigenvalue. You can see that the eigenvalues from our data all exceed the randomly generated eigenvalues that we have right here. The fourth and the fifth one, the randomly generated eigenvalues, are also, you'll notice, will fall below the eigenvalues from our observed data. So there's the fourth one and the fifth one. Now notice, though, that the sixth one from our data is 1.332, and if we look here in our table, that value actually falls below the randomly generated eigenvalue, or the 95th percentile of the randomly generated eigenvalue. So what that means then is that we make the cut right here, and we retain a 5-component solution, and essentially shave off all of the remaining components. So that's basically how you would go about interpreting your parallel analysis. Now, we could also carry out our parallel analysis using factor analysis. So I'm going to go to dimension reduction factor. Under extraction, I'll click on method. We'll go to principal axis factoring. That's the most common. And then we'll click on continue and then on OK. And so scrolling down, you'll notice that basically we get eigenvalues. These are, again, from the PCA. The PCA is essentially functioning as sort of an initial pass, and when the eigenvalue cutoff rule is invoked, it's essentially using that set of eigenvalues that are retained from a PCA to force essentially a 7-factor solution, and then the principal axis solution is iterated, and then you have essentially these eigenvalues that are right here. So technically then the eigenvalues that you are obtaining in this here, where if we click on factors and we leave everything else the same, you're actually comparing the eigenvalues from this column right here against the eigenvalues that are appearing in this column in your SPSS output. Note too that obviously it's only giving us 7 eigenvalues. We could also increase that up to 1 less than the number of values, or number of observed variables. So I can actually go to fixed number of factors and click on factors to extract. We have 39 measured variables, so I'll just type in 38, and so then I can get eigenvalues up to that point. And then theoretically then I could compare all those eigenvalues against the randomly generated ones. So you'll notice though that when we do this, the eigenvalues from our data actually exceed all of these values, and you even have some negative eigenvalues down here. And so that's kind of one of the limitations of doing the parallel analysis when you're working with something like principal axis factoring and basically standard factor analysis. It's been my experience that we oftentimes end up with a situation where there's considerable overfactoring, and so oftentimes it's a better bet just to stick with going with the principal components solution, comparing the eigenvalues that we have, in this column right here against the eigenvalues that are appearing, based on the principal components solution over in this area right here. So these eigenvalues here. So anyway, that's, so if we were to do that, based on our conclusion, then we would estimate, the presence of 5 factors, and then we could utilize that to force essentially a 5-factor solution associated with the principal axis factor analysis. So that is just a very quick overview of the use of this particular engine that's online, and it's like I said, it's really handy if you're using SPSS and you need something that's kind of quick, or something that works pretty well in terms of carrying out the parallel analysis. Like I said, I have another video that demonstrates the use of Brian O'Connor's SPSS syntax, and that's also an option as well. So either of these should work fine when you're carrying out parallel analysis, and in particular when you're working with SPSS.